is gaining strength. We have hopes that through MEMS, a lot of exciting missions will be accomplished in the future. If one goes all the way to Mars, every gram really counts. So at the end of the day, you might be having only a few kilos, and the idea is with those few kilos, what can you achieve in terms of possibilities? And certainly MEMS is an area which allows some possibilities. Some words on the materials structures, again here, just for the reference, and allows you to look into sort of which are leading providers in this domain. Things like, say, SIG type of materials, been a lot of breakthrough. There again, that shows you what one is trying to achieve by, say, having the materials, but also the manufacturing itself, how things look up. In the solar generators, certainly is something very important, where, of course, materials themselves are important. There's been a lot of difficulties in having substrates deforming. Certainly, the area of solar generators, there's still some improvements to be made. Just to give you some elements of accuracy also in terms of performance, you'll be talking of 0.07 millimeters in things of, say, little plates of 100 millimeters. Again, one is looking up at difficulties of materials, maintaining performances. In the area of thermal subsystems, and I must say in the UK, both people in Stevenage and RAL, say what is called now Astrium Stevenage RAL and RAL, there have been a lot of innovative developments in the areas of coolers, microprocessors, the compressors, and I think in this domain, again, materials are very important, and it's an evolving field. If you're going to have sensitive cameras, the thermal field, thermal control is very important. This is, again, a very important domain. Superconductivity is appearing as an important field, certainly also for terrestrial application, even so in space applications. So there's certainly every direction one turns, material is a driver, and in some cases it might be the breakthrough enabling part. If we're going to have, say, breakthroughs in superconductivity, say high temperature superconductor, certainly is going to be a major breakthrough also in space applications. In the area of propulsion, I would say is no other area which is materials as important, and this is, I think, some typical examples here. Propulsion system we have for new satellites, also like the Alpha Bus, where we have bladders to press the propellant. Certainly, say, materials don't like to be in an aggressive contact with, say, propellants, and we had difficulties in Europe to come and have the right materials. We still had to come up and bring solutions from outside Europe. I think here again, I'm sure there is the biggest invention still waiting on the shelf for people to figure out what's available and come and bring it in. And I really commend very much for people to look up in this domain. It's fair also to mention that in propulsion, like in any other domain, is not only the materials per se, the manufacturing process, how you combining materials, high pressure cryogenic tanks. You have wrapped up tanks with titanium insulators. People want to move up into a complete thermoplastic plus wrap up configurations. Quality, behavior, different temperature regimes are very important. Again, that one is talking up improvement in certain domains might be allowing in the range of 5 tons on an Ariane to increase by another 500 kilos. So again, there's a lot of innovation still to be brought in, and maximum use as different material properties improve right across the border. This is some of the elements I mentioned. In the area of, say, shared memory alloys, certainly a lot of benefits to be gained. One can utilize such materials in releasing, say, contacts at interfaces without generating shocks. Improvement in that domain, improving certainly an important domain. Just some words on in the area of optics. I already mentioned some things on that. A lot of innovation. I think for you just to get a feeling on the sensitivity, some years back we had a mission on the XMM where people trying to get the mirrors were sort of concentric cylinders that tried just to do with composites, gold plating, and at the end that technology had to be abandoned. And then one was talking of say the size of the fiber itself, it was degrading the experiment. So this is really done the accuracies you're talking. At the end, at that time, it was nickel electric forming technology was used to come up with the right finishing. What is looked now is to do also with more conventional type of innovative applications here. This is some, say, vegetation type of payload which has been looked upon, trying to use more classical aluminum with very high polishing. Again, there you're talking sort of an instrument where up to a few years ago would have been more like something 150 kilos. We're trying to reduce it less than 30 through some of the innovative use of materials. In terms of trying to keep up shape, rather than only trying to have up front before one flies, is to have in a smart application to allow through use of actuators, controlling the surface. This is something which has been discussed for many times, many years. I remember when I was at school, having smart materials, smart wings has been discussed. The fact of life still, people like to have something where interference at a later stage in orbit, if it could be avoided, it would be something preferable. However, as we try to, say, improve accuracies, this might be also enabling that there is so much you can improve, and then through active means in service, you can go one step beyond. Now, first of all, I'd like to think, just running in time, just coming half an hour through, I tried to explain some of the things we're doing, try to give some broad use of where materials go into. I hope I've not failed in the process in providing some of those details. However, I feel also the view graphs which would be available to you provides the width and in many cases the depth of some of the things we're looking at. As I mentioned, there is other angles of these subjects that have not been addressed here. For example, experimenting for medicine in orbit, growth of crystals. There is one activity I've been involved. It's been a combined ESA-EU activity, improving materials for, say, blades in jetliner engines, where Rolls-Royce has been involved looking up, can we produce high-quality materials which would go into the blades. Some of these specific aspects of microgravity have been mentioned here. I think, for me, there is no escape. Looking at design is to have a vision what we're designing, having a good definition of the load cases, and load cases include also the aggressive operational environment once we're in orbit, but also covering, say, the environment during takeoff. Space station in its life would experience something like 200,000 cycles of thermocycling. This is also an important parameter. If you have things which crack, certainly we keep cracking. After a while, you won't have something left. So these are all important parameters. However, the world moves on. New applications come in. Many areas, the consumer world, the automotive world, having breakthroughs, and we're certainly trying to keep up on that. Anybody who would try to be, say, also getting involved. Space is something which appears exotic and exclusive to few, but I think there is far more into it. And certainly looking at the audience here, I like to think that you find some of the elements here interesting, which I try to present. Again, very much indebted here to good friends invited me to be here. I'm very honored to be here and give this keynote here today. Thank you.